So I really wanted to kind of take home this example and kind of take a look at domain and range and the difference between, whole numbers and real numbers and what that does to domain and range. So kind of from my last video, we described a little bit about what whole numbers were. It included 0, went up by 1 each time. It was kind of like the natural numbers, like the counting numbers, but including 0 into it. So that's kind of what we see with this graph on the left here. We see discrete data. That's first off what we want to make sure that we know about this. This is discrete. Our domain values, we can see, are listed as our independent axis, our x-axis, going up by 1 each time on our horizontal axis. We see that each marker or each box is worth 1, so 1, 2, 3, 4, all the way up. So we have our domain as brace, open brace, 0, 1, 2, dot, 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 listing that. As if this were to continue going on. I just made the judgment call that this list was going to keep on going, and I decided to not cap it off just after 4. The range, if you remember from the question in the textbook, is just doubling all of our numbers. So y is equal to 2x. So we take x, we double it, and we get a range value. Hence, when x is 0, y is still 0. When x is 1, y is 2, 2 to 4, 3 to 6, 4 to 8, and it kept on going. So we have this relationship between the two, and again, for whole numbers, we're using a discrete method of giving or stating the domain and range. So that's one of the things that is kind of like a big picture idea when it comes to that. Discrete, your domain and range are going to be listed as, values as you go ahead. Again, it's always going to be from least to greatest, just as we normally would, but for discrete, we have this. Now, here's the issue. When we go for continuous data, we have to use a line. Continuous data, and let's say that we're doing real numbers, and for this case, I'm just going to say real numbers that are greater than 0. I think I should have put that into the question as well, but I'll say it now anyways. Real numbers that are greater than 0. And we see that now these discrete data points that we had before, which is following the same equation, as you can see, and by the way, they're also functions. But following the same equation, we are just now connecting these with a line. And of course, we have an arrowhead at the top stating that it's going to keep on going forever and ever. Much like we did with the 3 ellipses or the 3 dots that we have here. That's kind of like the equivalent in terms of domain and range, but for a continuous data set. So we have continuous when we use our line. This is continuous. I'll try to fit that in there. So when we do a continuous data set, then we have to kind of change up the way that we are approaching domain and range. Now, there's always going to be 2 different types of notation that you can use. And one of them is used more so for applied, and the other one, well, can be used for pre-cal and applied. In this course, we do both because who knows where you're going to end up. Maybe you'll go to applied, maybe you go to pre-cal, maybe you go both. Doesn't really matter. But you have to know how to do both. So for continuous, then this is where we have to kind of get into talking about domain and range. And we're going to be talking about set notation versus interval. Now, I'm going to get you to always kind of take a look at those notes, read those notes through, and this is going to provide you a little bit of extra examples with it. When we're looking at our domain, I went through like the perfect mathematics way to use the set notation. I really don't expect anybody to do that. It's pretty... I don't really know why any of you would want to do it that way when we can just kind of cut it down a little bit and make it a little bit more streamlined for yourselves. If you want to do it the perfect mathematics way, go ahead. I listed in the notes of how you can do that. But for set notation for domain, what we're going to do here is we're going to list out what all of the x values can be. And normally for domain, we would go from least to greatest. But in this case, when we're using our variable x, we want to kind of state that first. So we could go and have our domain as 0 is less than or equal to x, and that would be fine for our domain. But typically speaking, if we only have one inequality like we see here, we're actually going to start with our variable first. So it would be better for us to say x is greater than or equal to 0. And that could be our set notation for domain for a continuous function, like we see on our graph to the right. Now, if we're going to use interval notation, which is completely fine. Interval notation is awesome. I love interval notation. But then we would go and we'd start from our lowest value of x, which is 0, to our highest value of x, which is infinity. Now, I'm using the inclusive brackets here because I can equal x, or I can equal 0. I can equal 0. Now, so I'm using my inclusive brackets, the square brackets. Now, infinity, remember how I said that we can't actually equal infinity, it's more of a concept? Well, that's exactly why we're using the curved brackets here, or the non-inclusive brackets. Can't equal infinity. So I'm just going to leave it as my, I call them round brackets, but they're non-inclusive brackets. So we have set notation for domain for a continuous data, or for continuous function. X is greater than or equal to 0, and that's based upon our graph, based upon our domain. Or in interval notation, we can do this. Now, our range is going to be the same in this case. There's not going to be any difference between it, which is interesting because when we used our discrete data, our range was definitely different than our domain because it had to be doubled. But since we have infinite values in a continuous data set, our range is going to be, in this case anyways, is going to be exactly the same. So we would start off by saying y is greater than or equal to 0. My lowest y coordinate is 0. Same with my x, right? Or, just like before, in interval notation, 0 to infinity. Inclusive for 0 because we can have a y coordinate of 0. Non-inclusive for infinity because we can't equal 0. Oh my gosh, Artie, chill, buddy. So we have our domain and range for our continuous data set. The only reason why I'm saying that it's going to infinity is because we have that arrowhead shooting up towards infinity. This is going to positive infinity for x and positive infinity of y. Kind of imagine going off the screen, right? Going up and up and up off your screen. It's going up and up and up and up and up, which means that we're going to get to our y value of infinity, or approach it anyways. But it's also going towards the right. And towards the right, there are higher and higher and higher x values. So we're going to get to that infinity for our x values as well. These infinities only occur when we're dealing with interval notation. You would never have infinities when you're dealing with set notation because we use our inequalities instead. We don't use infinities in set notation. We use our inequalities to show that, hey, x has to be greater than or very minimally equal to 0. So we can go up and up and up and up and up. Same with y. But for interval notation, then we do use the infinities to represent where we would stop this function. That's a little bit more about domain and range, difference between discrete and continuous, and how we kind of do that data set.